Hello, this will be a demonstration of proposition 24 from book 3 of Euclid's Elements, which states that similar segments on equal straight lines are equal to one another. What we are given are the equal straight lines AB and CD. And these straight lines AB and CD are equal to one another. And on AB, we have the segment of the circle AEB, like so. And we have a similar segment on the straight line CD, like so. And these segments, these similar segments, with the segment AEB on the straight line AB and CFD on the straight line CD. Now, given that this is all the case, that AB is equal to CD, and the segment AEB is similar to the segment CFD, what we've set out to prove is that the segment AEB is equal to the segment CFD, that these two similar segments on equal straight lines are equal to one another. We did this first by engaging in a process of application. We saw this in proposition 1.4 and 1.8, and I do believe this is the final time that Euclid employs it in the elements. Now, if we apply the entire area of the segment AEB to the entire area of CFD, and if we apply the point A to the point C and the straight line AB to the straight line C, so that would look something like bringing A down to C, and the whole straight line AB down to the straight line CD, like so, and the whole area of the segment AEB to the whole area of the segment CFD. This is done so that, like, if your segments are like that, where one is like something like that, it's still on an equal straight line and it's still similar. Euclid adds that step of applying the areas to circumvent that issue. Now, if we apply one extremity to the other, so if we apply A to C, these are both extremities of the straight lines AB and CD respectively, and we apply the whole straight line AB to the whole straight line CD, then by virtue of what it means for lines to be equal, which is that the distance between their extremities are equal, we know that the point B must then coincide with the point D. Again, this is by virtue of what it means for straight lines to be equal. And so, having done all of that, applied the area of the segment AEB to the area of the segment CFD, having applied the point A to the point C, and the straight line AB to the point, to the straight line AB to the straight line CD, and now knowing that the point B must coincide with the point D, we're then left with 4 possibilities for how these two segments can now relate to each other. Now, if they do not coincide, then, so if it is the case that the segment AEB does not coincide with the segment CFD, the only other 3 possibilities are that the segment AEB falls within the segment CFD, that the segment AEB falls outside the segment CFD, or it falls awry, some parts being inside and some parts being outside. Now, first, let's tackle the case in which one segment falls inside the other. So if the segment AEB falls inside the segment CFD, this will look something like that, okay? So you have the whole segment CFD like so, and then you have the segment AEB inside of it. Now, if the segment AEB falls within CFD, if it's inside the segment CFD, then these two segments cannot be equal. We know this by common notion 5. Looking here, one segment has to be a part of the other. By common notion 5, we know that the whole must be greater than the part and the part less than the whole. And finally, that parts and wholes cannot be equal, or parts and wholes of the same thing cannot be equal. And so, segment AEB being a part of the segment CFD cannot be equal to it. But we also know by proposition 3.23 that you cannot, on the same straight line, describe two similar and unequal segments. We know that the segment AEB cannot be unequal to the segment CFD. That would be contrary to proposition 3.23. And so we see that the segment AEB, if it falls within the segment CFD, must simultaneously be unequal and not unequal to the segment CFD, which is obviously absurd. And so we can dismiss the case that the segment AEB falls within the segment CFD entirely. So we don't have to deal with this anymore. Now we can do a similar thing if the segment AEB falls outside of it. So this would look something like that. So you have the segment AEB over the top of the segment CFD. This is what it means for it to fall outside. And by a similar process, we know that the segment AEB cannot be equal to the segment CFD because CFD is now a part of AEB. And so they're unequal, but we know that they can't, but we also know that they're not unequal by proposition 323. So we end up with, again, this contradiction that the segment AEB must simultaneously be unequal to and not unequal to the segment CFD, which is obviously absurd. So we can dismiss, again, the case that the segment AEB falls outside the segment CFD. We don't have to consider that. Now the final case, if they don't coincide, is that they fall awry. This would look something like that, right? Where you have a part of the segment inside the other and another part outside of it like that. Now, if this is the case, then the whole circle of which the segment AEB is a part of cuts the whole circle of which the segment CFD is a part of, right? We see this here. They share 3 points like so. They share that point, they share that point, and they share that point. And so if we consider the whole circles of which these segments are parts, then the two circles, the circle ABE and the circle CFD, must cut each other at more than 2 points. They evidently cut each other at 3 points, right? We have 1, 2, 3. They cut each other at 3 points if we describe the whole circle. However, by proposition 310, we know that two circles cannot cut each other at more than 2 points. And so the circle AEB, of which the segment AEB is a part of, cuts the circle CFD, of which the segment CFD is a part of, at more than 2 points, but it also does not cut it at more than 2 points. So this is an obvious contradiction that it cuts it at more than 2 points, but it also doesn't cut it at more than 2 points. This is obviously an absurd thing, so we can dismiss the case that it falls awry. And so the segment AEB will not fall awry from the segment CFD. So we will not have something that looks like this. Okay, well, these are the only 4 possibilities after having gone through this process of application are that the two segments coincide, one falls within the other, one falls outside the other, and one falls awry from the other, or they coincide. We've dismissed 3 of the 4 cases, and so the remaining one must be the truth. And so, knowing that the segment AEB falls neither within the segment CFD, nor outside it, nor awry from it, they must coincide. So the segment AEB will coincide with the segment CFD, and things which coincide must be equal. That's common notion 4. And so the segment AEB coinciding with the segment CFD must be equal to it. And we have accomplished what we set out to prove. We have set out to prove that the segment AEB is equal to the segment CFD. And this being what we set out to prove, we are done with the proposition, therefore, etc. QED. I hope you enjoyed application while it lasts, because this is the last time it is used in the elements. Other than that, I have nothing to say about this proposition, so I will move on to 325.